So let us consider y2 plus py1 plus qy is equal to r as the second order linear differential equation with variable coefficients. That is, the coefficient of y1 p and the coefficient of y q are functions of x. The derivatives y2 d square y by dx square, y1 is dy by dx, is also derivative with respect to the independent variable x. To solve such problems, one of the technique is to reduce the given differential equation to a second order linear differential equation with constant coefficients. That is, we need to change the coefficients of y1 and y as constants. For this, we need to find the new variable z. Suppose we change the variable x to z, then the first order derivative y1 will be y1 is equal to dy by dx. It can be written as dy by dz into dz by dx. So here z1 stands for dz by dx. So I can write y1 is equal to dy by dx into z1. And y2 will be d square y by dx square. It can be written as d square y by dz square into z1 square plus dy by dz into z2. So we'll make the substitutions for y1 and y2 in the given differential equation. With this substitution, the given differential equation can be written as d square y by dz square plus z2 plus pz1 divided by z1 square into dy by dz plus q divided by z1 square into y is equal to r divided by z1 square. And this can be written as y double dash plus p1 into y dash plus q1 into y is equal to r1, where we have taken p1 is equal to z2 plus pz1 divided by z1 square, q1 is equal to q divided by z1 square, and r1 is equal to r divided by z1 square. Y double dash will denote the derivative with respect to the new variable z, that is d square y by dz square. Y dash will be dy by dz. So we need to find the new variable z as a function of x. For this we retain two techniques. One, the first technique, we let q1 as constant. q1 is equal to q divided by z1 square. We let this as a constant. And from this one, we can extract z1 as z1 square is equal to q divided by q1, and then we can write z1 and also z. After finding z1 value, p1 may become 0 or constant. By proper substitution for z2 and z1, p1 may become 0 or constant. So in the first technique, we retain q1 as constant and make p1 as 0. In the second constant, we may set in the second method we may set p1 is equal to 0 and q1 can be reduced to constant. Again, when we write p1 is equal to 0, we see that the numerator of p1, that is z2 plus pz1 is equal to 0, or we can rewrite it as z2 is equal to minus pz1, or z2 by z1 is equal to minus p. And from this equation, z2 divided by z1 is equal to minus p, we can find out the value of z1 and hence z. So we can find the p1 value, z1 value, and q1, it may reduces to constant. So overall, our intention is only to reduce the p1 q1 as constants or 0. So let us understand the same method by taking one example. Solve d square y by dx square minus cot x into dy by dx minus y into sin square x is equal to cos x minus cos cube x by changing the independent variable. Now the given differential equation is d square y by dx square minus cot x into dy by dx minus y into sin square x is equal to cos x minus cos cube x. Here we know that the coefficient of d square y by dx square is 1. So we can directly identify the coefficient of y as p, the coefficient of y1 as p, the coefficient of y as q, and the RHS as r. So we write p is equal to minus cot x, q is equal to minus sin square x, and r is equal to cos x minus cos cube x. R is equal to cos x minus cos cube x. Now r can also be written as cos x into bracket 1 minus cos square x or cos x into sin square x. We need to change the variable x to the new variable z. For this, we first set q1 as a constant. So let us write q1 as the coefficient of sin square x, that is minus 1. q1 is equal to minus 1. Hence by the equation q1 is equal to q divided by z1 square, we see that z1 square is equal to q divided by q1, or we have z1 square is equal to sin square x, and this implies z1 is equal to sin x. So when you have z1, that is dz by dx, dz by dx is equal to sin x, z is equal to minus cos x, and z2 is equal to cos x, that is d square z divided by dx square is cos x. With these values, q1 is equal to minus 1 and z2 is equal to cos x, z1 is equal to sin x. We substitute in the p1. p1 is equal to z2 plus pz1 divided by z1 square, that can be written as cos x minus cot x into sin x divided by sin square x, and the numerator becomes 0, so p1 is 0. And r1 is equal to r divided by z1 square. As I told earlier, r is cos x into sin square x, z1 square is sin square x, so r divided by z1 square is equal to cos x. So the value of q1 is minus 1, p1 is equal to 0, and r1 is equal to cos x. Now we are changing the coefficients and also the derivative y1, y2 with respect to z. So in the equation, in the entire equation, we need to retain only the functions of z and the derivative with respect to z. So the r, value of r is cos x, even though cos x, we retain it as a function of z, that is we write it as minus z. So the new reduced differential equation is y double dash minus y is equal to minus z. Here y double dash denotes d square y by dz square, or d square y by dz square minus y is equal to minus z. And the solution of this equation 2 has complementary function as well as particular integral. So for the complementary function, we write the auxiliary equation d square minus 1 is equal to 0, or this implies d is equal to plus or minus 1. Hence we have the complementary function as c1 into e power z plus c2 into e power minus z. And for the particular integral, we consider 1 divided by d square minus 1 into minus z, or again it can be written as 1 divided by 1 minus d square into z, or it can be written as 1 minus d square to the power minus 1 into z. And using the binomial expression 1 minus d square to the power minus 1 can be written as 1 plus d square plus d to the power 4 plus 1. So we write 1 minus d square to the power minus 1 into z as 1 plus d square plus d to the power 4 plus 1 into z, and the second order derivative and higher order derivative of z is 0. So we have only z. So the particular integral is z. So thus the complete solution of 2 is y of z is equal to c1 into e power z plus c2 into e power minus z plus z. And again substituting z is equal to cos x, we can change y as a function of x. So we write y of x is equal to c1 into e power minus cos x plus c2 into e power cos x minus cos x as the complete solution of given differential equation.